Okay, in this video I'm going to talk a little bit about another example, the third example of how to use genetic algorithms and evolutionary solvers in order to augment your tool. And in this case I'm using the voxelizer and modifying it so that using evolutionary algorithms I can take out certain parts of voxels uh, within this geometry that fall under certain conditions. For example, the example I'm using in this case is if I'm assuming that each of these blocks is a single unit, I'm going to try to detect the blocks that are filled in on all 6 sides or 5 sides, and I'll remove them so that I can try to have these units that are always exposed to the outside or always have an outside window. You can imagine that that applied to a series of, like a real series of units, would then create these logics of porosity that would then enable you to augment your design. Or augment or alter your design. So, just a little sneak peek. Again, I'm using the Voxelizer program, and actually this is after having run it. You can see these two holes are actually a result of what happens, and let's see if I can show you. These red portions are the boxes that were removed because they were surrounded in on too many different sides. Now this is looks like an anomaly, but this box, that box, and to some extent these two boxes were removed because they were boxed in on too many sides. There are also boxes inside of here that you can't see that are being removed because of the same. So I'm going to talk about how to get there from scratch, but I'm actually going to start from the voxelizer example. And if you don't know how to get there, then I would suggest that you watch the other voxelizer video. So here we have the voxelizer, and just going to move it around until we have pretty good form. So we have the voxelizer, which basically takes a given object and divides it into chunks, or pixels, or voxels, 3D pixels. And instead of dividing them and banding them, I'm just going to all color them uniformly. So I have the voxelizer script, and what I'm going to do is I'm just going to grab the initial points, which are over here. So this is an example in which, given a specific tool or an existing tool, I'm going to do an analysis on top of it. So the analysis I'm going to do is, given a point, how many points or how many boxes, given a box, how many boxes is it touching? Now the real question is, how can we calculate that? It seems like a little hard to calculate. But if you think about it, all of these points, because we've generated them, are equidistant to each other. They're equidistant to each other based on a specific distance, that distance being, I believe, this number 5.085. Yes, that's true. So this is the number between all of these points. And so that thus means that any two points that are exactly this distance apart are adjacent to each other. That's because if they're at a diagonal, right, then they'll be more than this distance apart. So if two boxes, or the center point of two boxes, are exactly this value, say in this case 4.853, if they're exactly 4.853 units or inches or meters, what have you not, apart in space, then they're right next to each other. So the question is really trying to get the distance between, trying to find the distance between this point and all the other points in this set of points, and figuring out, okay, how many points are exactly this distance apart. And in some way, it's a very simple way to figure out, okay, that means that if we have 6 points that are 4.853 units apart, then this box is probably surrounded on all 6 sides. So let's do that. How do we do that? Now, first of all, we have this geometry, and we want to compare it against all the other points. So what I'm going to do is I'm going to graph itself, grab itself, and I'm going to use a line. And so, just so I can visualize what's going on here. Now, this is making a lot of lines. This is making 15,000 lines, and that's how many connections are between this point and everything else. Now, if we were smart about this, we would probably be able to actually just only look at the points in its vicinity. But lines are pretty fast. Notice that it's only taking us 36 milliseconds to draw all these lines. And I'm going to bet distances are even faster than lines. 21 milliseconds. So it's pretty trivial to go through and calculate all the distances. So we're not going to worry about just, grabbing all the points near it, because that requires a degree of calculation that's maybe more trouble than it's worth, or it was just too slow. So you notice that already, if I look at it, I get one point that's 0.0 points distance away, and 2 points that are 4.8 units away. And the 0 distance away, that must be because we're comparing a point against itself. That's pretty funny. And then we have all these other distances. So I'm going to say, okay, I want to find when the distance is actually just equal to our number. And then if I find that value, I get all these true-false values, which is great. What that means is I can use a dispatch function based on those true-false values to filter out for the list of points. Let's try that again. That means that if I see only the true, then for the first point, let me just simplify this in this list, it finds 3 points that are exactly 4.853 distances away. And some points have 5 points that units away, or some points have 3, etc. Some points probably have none. And so as far as we're concerned, we're not really interested in what the exact points are. We're just interested in how many there are. So I'm going to use the list length function and plug that in. So if I also see what's going on there, and there we go. We get the number of points nearby, which pretty much equals to, given any box, these are how many boxes are surrounding it. And since we're using a voxelizer, probably the minimum number of voxels next to it, voxels next to a voxel is 1, so we probably get 1 at the very end. Maybe that's this top one. And I'm going to flatten this out. So this is great. I have 126 values that note how many faces 126 of these boxes are adjacent to. And I can actually, what I'm going to do, I'm going to do a really quick preview thing. So I'm going to use a custom preview, and while I'm at it, I'm actually going to turn the timer off, just so that we're a little bit snappier. Okay, great. So I'm just going to check out the timer. Okay. So I'm actually going to use a custom preview component, because it'd be nice to see actually a little indicator of that. How many boxes is everything adjacent to. So I'm going to use the bounds component to get the bounds domain. So we have 1 to 6. I'm going to use the remap numbers component to grab this list of lengths according to the source domain. And so now we have them cast as numbers between 0 and 1. And then I'm going to use the color RGB function to color code the different boxes. Which boxes? We're getting these boxes. And notice that right now we're using 126 points, and here we're getting 106 boxes. Because the points drive the boxes, they're in the exact same order, so we can use these boxes to be colored with the preview. And behold, we have a little representation. In fact, let me just work in here. So the darkest boxes are the least adjacent to things, and the lightest boxes are the most. This is a little confusing, so I'm actually going to invert the relationship. So the lightest boxes are the most exposed, and the darkest boxes are the least exposed. So this makes sense, right? Because this box is boxed in on all 5 sides except for this side that we can see. And it's pretty fun. It's a pretty fun analysis. So now, let's say our motive is we want to, and let me actually make a more regular looking structure. So just for the sake of this, I'm going to make, kind of like a box-like form. Okay, great. This is a little better. It's kind of a lot, but it's alright. I'm going to make a box-like form, and let's see, we're actually dealing with 287 boxes. That's okay. So going back to this length component, let's say we want to find all the boxes that are more than 4, and we want to remove them. So I'm going to say, okay, which boxes are boxed in on more than 4 sides? Whoops. So this is going to give me a list of true-false values. I'm going to use this dispatch function, and then I'm just going to move everything down a little bit. And I'm going to use this dispatch to sort between the boxes. So that way, and I'm going to actually disable this chunk because this was part of the voxelizer that was dividing the voxels into different portions, but I'm not really interested in that. What I am interested in is just grabbing those parts that are less than 4, or boxed in, sorry, more than 4. Boxed in more than 4 sides. So I use that preview function to show it. Here are all the boxes that are boxed in on more than 4 sides. Here are all the boxes that are not. So if I'm going to go in and kind of hide everything. Excellent. And I'm going to also hide this geometry. So then, right now you see the shell because I have grabbed all the boxes. This is pretty interesting, in fact, on its own. I didn't realize I would get this result. I'm deleting all the boxes that are boxed in on 4 sides. This is 4 or more sides. Depending on this number, you can see that actually, because I'm getting the B outlet, this is all the blocks that are not boxed in on 4 or more sides, which makes sense because in higher put it, it's dividing it into objects that are boxed in on 5 or more sides and objects that are boxed in on 4 or less sides, 4 or fewer sides. Now, but the thing about this is that once I start doing this, I get this large hollow empty thing, but that doesn't make sense because if I removed one of these, let's say I removed, in fact, let's say I was looking at everything, and I remove this corner box. If I remove this corner box, all of a sudden that affects the boxes around here also. So what I don't want is to just remove everything that is boxed in, because by removing one, all the other ones might become tolerable. So I can't just go in and sift through and remove everything. I have to kind of strategically remove a number of boxes, and that's where Galapagos comes in and can help us. I'm actually going to move these dots a little south so we're working with a more manageable number. I'm actually going to increase this a little bit so we're also still working with a more manageable number. Again, it's easier to try it out with more manageable numbers first and then go more detailed later. Okay, great. So let's try this out. So what's our process? Well, I'm going to use the gene pool because it has a bunch of sliders, and I'm actually going to set them from 0 to 1, and I'm going to make the decimal count high. And the reason why that is this gene pool, while we're using it as, it's giving us a number of points between 0 to 1, I'm actually going to use it to choose out of the list. So 1 is going to choose the last number of the list, 0 is going to choose the first number of the list, 0.5 is going to choose the middle one of the list. That way, I'm not dependent on, I can choose a specific item out of the list without having to always set the maximum number of boxes, if that makes sense. So I can move the slider and the gene pool, this thing will still make sense. So I'm going to grab the list length. So I want to know how many points I have in general. How many points do I have in general? I have 48 points, or 48 boxes. I'm going to multiply these two together. So that kind of gives me an approximation of what number. And then I'm going to use a round component. I'm going to use the floor component. The reason I'm using the floor is because in Grasshopper, lists start from 0. So if I use a round up, I'll never get this. I'll never hit the 0th one, because even 0.1 will round up to 1. So I'm using the floor component, so I can also include 1. So 0, the 0th item, or the first item with on index 0. So now you can see this is my list of which items I'm choosing, and I can choose to select 50, or I can choose to select, I don't know, 30. I'm going to set this at 11 or 10. So these are the items I want, and I'm actually going to use the list item then component. So out of the list of boxes, I want to grab these boxes, setting those as the index. So arbitrarily speaking, they're these. And so depending on how to remove the slider, I'm moving one of the boxes. So you can see that now this is a way to remove some of the boxes. Now, right now I've selected the boxes. How do I remove the boxes? Well, one component that's helpful is I can use replace items. So I can grab the boxes, and I can replace them with nulls or nothing. So if I do the same thing, I'm going to replace these indices. You can see that all the nulls are fitted in here. That's okay, because that just means that so then now I have a form with a series of holes, and when it's null, then nothing goes in there. That's great. Okay, actually what I want to do is not actually plug the boxes in. Well, actually, that's okay. I do want to plug the boxes in. But what I want to do is I want to then use this geometry and then calculate how many boxes are boxed in, or what the metric is of general boxed inness. So in fact, yes, I actually do not want to use a box. I want to do it on the initial points. And so what I am going to do then is I'm going to move this part, all these things, all the way over here. So I have the gene pool, I'm getting the number of points, and then I'm going to replace the points using the gene pool with these numbers. In other words, I'm going to remove points from the list, and this is a way that I can remove a specific number of points. Let's say 20 points. And so now I have my new list of points. Excellent. And in fact, if I don't want these nulls, and right now I don't, because it'll make things messy, I can use clean trees. If I plug it in here, then it'll remove all the null items. That's exactly what we want. So now, this is in fact our new list of points. And then on top of these points, we want to do the analysis of proximity and all these kind of things. So in fact, I'm going to plug this into all the areas in which those original points are plugged into. I have these points. I'm doing the exact same process, and I'm still getting the points that are 2 boxed in. So these are the points that are boxed in on 4 or more sides. And then without those, these are the points that are not boxed in. So I'm actually going to represent just those in the preview. So if I unhighlight, and it looks like there's some other things that I need to hide. some other things that I need to hide somewhere. Let's see. Whoops. What's being hidden? Something is being colored in not an ideal way. How can we see that? Okay, it looks like something going here. Oh, this thing. Great. It's a little hard to see. Oh, there we go. So what's going on? Oh, and right now I need to delete that aspect. Okay, so great. So what we're doing is we're moving a series of boxes and trying to calculate if the units are ideal or not, or how many units are being boxed in. And you can see over here that we have found that in this scenario, there are 14 units that are boxed in on 4 or more sides. There are no units that are boxed in on 5 or more sides, which is great. But let's say we want to eliminate the number of units that are boxed in on 4 or more sides. So we have these boxes, and what we really want is just the number. We want how many units are boxed in on 4 or more sides. Right now it's 15. But if we randomize that initial list and change how many points we take out, or what kind of points we take out, that might be 4. So great, on this scenario, there are only 4 boxes that are boxed in on 4 or more sides. So now you get the gist of it. This is actually a metric. This is our fitness function. I'm going to group it. And let's try using Galapagos. The fitness is this number. And then I'm going to use the genome and follow this control this gene pool. So to recap, I'm controlling the gene pool, which is the box to take out. And according to that, it's going to calculate how many boxes are being boxed in what way. And this is actually not that helpful of a way to visualize this. So what I'm going to do is I'm going to show both the deleted and the non-deleted parts by using a color swatch. I'll do this, and I'll make the swatch red with a lot of transparency, maybe even 0 transparency or a tiny bit. So now you see that these red boxes are the portions that are being deleted. And the other aspect of this all is that it's really hard to see what's inside. So what I'm actually going to do is I am going to make the boxes smaller than they need to be. Kind of like that. Which is nice. And in fact, I'm going to do this twice. You'll start to see why. Now I have the full boxes, and I'm going to get the brep, deconstruct brep, deconstruct box, deconstruct brep, and then I'm just going to get the edges. And in fact, I think I can get brep edges. Let's try that instead. Naked edge curves, interior curves. We want that. And we just want to flatten them, and we're really not really interested in how many there are. So this is kind of a helpful thing. I thought that we could just visualize the box grid as well. Perhaps this is helpful. And I'm going to make this into a floating point. So by going like this, I can kind of see what's inside and what was removed. So you can see here that this box was removed in there, and that's pretty helpful. Okay, so now I'm going to try to run this. Recap. The Galapagos is controlling these dots, so it's controlling which boxes are being removed. And then it's giving us a number of and it's going to do that by trying to minimize the number of boxes that are boxed in. So we can double click and click on minimize, and let's see it go. It's going to iterate through all the possibilities. And so my hope is that it removes enough boxes that it minimizes the number of boxes that are boxed in on 4 sides or more. So it's kind of trying to create a certain kind of porosity. And let's see how that goes. So I'm going to fast forward to 5 minutes into the future. Okay, great. So lo and behold, it looks like it's kind of stopped at 0, or we have a lot of 0 solutions. So I'm going to look at this. So now, according to our calculations, we have 0 boxes that are boxed in on 4 or more sides, which is pretty amazing and pretty great. Let's see, I'm going to grab that geometry and just bake it out so we can see what's going on in Rhino. And let's see. Kind of looks like that's the case. A little bit, actually. This box kind of looks like it's boxed in on all sides. So you know what? Let's try that again. And let's go in, and we may have to engage in a little bit of debugging. So if I look at all the distances, and I'm graphing the distances between me and myself, I want to know whether it equals 7.298. And what I'm also going to do is I'm going to use the list item function and a slider. So I can choose one of the items, and I'm going to use a slider to grab this box, or perhaps grab this box. Oh, the other aspect that I just realized, and apologies for not catching this earlier, is we have a little bug because what happened when we cleaned the tree is that the order of our boxes has become drastically different. Right now, over here we have 30 boxes. Over here as an input we have 48, and we have 30 inputs. So the boxes, because the order and the number of the boxes didn't match the order and the number of the patterns, we get an incorrect kind of distribution. So that's not what we want to do, and in fact, what we want is these initial points, actually, just for the sake of representation. We want them, or the points that go into the plane that then drive the boxes, we want them to be driven by these points, the points after removal. That way, we have the points, we have those boxes. How many boxes do we have? We have 30 boxes, and those 30 boxes then matched up with this will give us the right answer. It looks like it may have already. So I'm going to unhighlight that and clean everything up a little bit by hiding previewing. And actually, if I kind of bring that back to 2, let's say just plug that back in, you can see that, yeah, now I do get the Swiss cheese hole. And in fact, it has removed boxes enough so that all boxes have at least 3 sides open to the air. That's a pretty interesting result. Why don't we try it on a slightly higher resolution? So I'm going to go like that. And correspondingly, I'm going to change the number of points we remove. I'm going to say we're going to remove 41 points because we already have 121 boxes. So let's say I remove 41 points, and I'm going to randomize the number of boxes I need. Okay, so let's try that again. I'll try the randomization again. Again, nothing has really changed, and maybe I'll actually play with my geometry a little bit. I'm going to go into the split perspective and maybe move that up. So a slightly different voxelization pattern. And then I'm going to try to use Galapagos to minimize again the number of boxes that are boxed in on 4 more sides, so that ideally I get all the boxes are open on at least 3 sides. So I'll let it run for about 5 more minutes. Here we'll check in for a moment to see how it's going. You can see that it's getting better and better. The average is actually going down, while the highest possible, the lowest possible example is it's getting better here. Actually, this top line, so this is a measure of how good our results are. So even though these numbers are going down, you can see that initially our value is 26 here. As we go onwards, this top line is relatively horizontal. That means that our best results, which is our fitness value being smaller, are plateauing here. Now, if our best results get even better, then the graph will change. So this is kind of our curve of performance, not our curve of fitness value. So even though we're minimizing our fitness function, the higher the curve goes, the better our optimization is performing. So you see that here we have a jump from 23 to 21. So now you can kind of chart out the progress of the fitness function. Another thing that we can do is, if you notice down here that all of the values are similar, because all of these genome graphs are kind of syncing. You kind of see, when you see all of them overlaid on top of each other, it means that they're all similar. And you can also see here that you have this one giant clump. So what I'm going to do is I'm going to press the randomize button. That means that in the next generation it's going to create a lot of more mutations in hopes of finding different possibilities a little bit more. I guess I'm diversifying the gene pool a little bit. Just to kind of shake things up and make sure. The other thing about genetic algorithms is they're not 100%, they're never always going to solve the problem. Or you might need to take a lot of time to solve the problem, or you might need to modify the parameters. So you see now here, having plugged that randomization in, our average performance dropped. That's maybe a necessity if you want to try to explore different possibilities. But again, a genetic algorithm isn't like a magic tool. It requires a lot of testing, and especially this kind of optimization where we're dealing with one value, we're just trying to minimize one value or not. There's a lot of different ways you can go about it, and there's an infinite amount of literature on these processes. But so if you find something that doesn't work, don't despair. Maybe leave it running for a while, or try to reformulate your metric. And you can already see that having left it running, our value has improved 17. So that's good. So I'll leave it running for 5 more minutes. Okay, so after about 30 minutes, 10 minutes, we've kind of arrived at this, way better. There are only 6 blocks that are boxed in on more than 3 sides, so I'm going to stop the solver now. This is after 125 generations. Reinstate that. And you can see this is what we get. I'm going to shrink the box a little so I can see what's going on. So it looks like, it's kind of made Swiss cheese of our building, or our mass, in an interesting way. And so you have all these holes and voids inside, which is one interesting way to deal with sunlight aperture. Now, you can imagine, so this is one way to work and kind of modify a massing, because you could start to re-rationalize this into a mass. Another idea is that you could gather the number of points that you've deleted and then kind of aggregate them on top, kind of recoup the FAR, and imagine a process in which the logic of porosity is maintaining the FAR while, again, exposing all blocks, or allowing blocks to be exposed to the air. This is another example in which this algorithm can be, the genetic algorithm solver can be more spatialized or more kind of incorporated into architecture.